Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video. All math-based, of course, and as always, it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Stepping aside, will you? We are concluding Chapter 2 in the Big Ideas Math Integrated Math 3 textbook with Section 2.7 on modeling with quadratic functions. Now, this chapter's been a little, the order's been interesting. We introduced everything with linear, constant, absolute value, and quadratic functions. Then we dived into a lot of things just linear or absolute value, including transformations of them and then modeling with them. And then lately we've gotten into the quadratic realm of transforming quadratic functions or transformations of them, characteristics of them, and now modeling with them. So we kind of introduced them all and then a block of one, block of the other, and that's the chapter. And I think it leans pretty well into Chapter 3, all told, which is pretty good. Ooh, big car wreck going on in the background. I don't know, someone's flipping down a cliff, it looks like. So enjoy that car wreck as we get into the car wreck of modeling with quadratic functions. Let's finish the chapter strong, guys. 37 questions with the lecture. Go ahead and download the PDF down below in the description section. If there's anything to graph, I'm going to provide graph paper attachments for you as well, and follow along the timestamps. We'll start with the lecture, go to the problem set after. Here we go. Let's hope we can save whoever's in that wreck later. All right. So we're going to learn how to write equations of quadratic functions using vertices, points, and x-intercepts. I think we've done some of that before, definitely done it in IM2, but I feel like I've done without some of the problems as well, at least writing vertex form. They're probably going to do all the different forms, and write quadratic equations to model data sets. So get your graphing calculators ready. We're probably going to have to use quadratic regression for that. All previous terms before, yes, we've talked about second differences and such. I can't remember the specific section that we did mention that, but yeah, first and second differences will come to mind here. Systems of three come back. Oh, that's to write equations in standard form. And the quadratic formula. All right, so reintroducing some things of old. Some of the stuff might be from IM2 even. Anyway, let's see what they're going to talk about. Writing quadratic equations. If you're given a point and the vertex, you might want to use vertex form. Yeah, this is the one I've done a couple times before. Plug in my h and k, plug in something for x and y, and find your a. I'll also do this without plugging it in, and I'll just use the graph as well. I'll show you both of those. I don't think we've done this one yet. We did it in IM2, but given a point and the x-intercept. So two different points, but they're specifically the x-intercept points. And then a third point, you can use x-intercept form as well. Plug in your p and q as your x-intercepts. Plug in the x and y values here to find your a. It's all about finding the stretch factor, basically. Writing the equation is find the stretch factor and let that work itself out. Given 3 points that are not necessarily vertex, not necessarily intercepts, right? You can set up a system of equations, a system of 3, and I guess that's a good reason why we had a whole section on that. We can solve it that way as well. So I'm sure they're going to do examples of all 3. We'll take a look at what they are, then we'll do them in the problem sets. All right, writing the equation using vertex and a point, and I will show you how I can do this in a graphing form based off what we've been doing on graphing. They're all one the same. The graph shows the parabolic path of a performer who is shot out of a cannon. So, where y is the height in feet, x is the horizontal distance traveled in feet. So they're literally going that way. They hit a max height here. That's considered the vertex. They say write an equation of the parabola. And then it says the performer lands in a net 90 feet from the cannon. What is the height of the net? So somewhere where x is 90, there's a net there it's catching it, right? So that's the second question after you've come up with the model. So what they're going to do is, and I like to do this kind of in 2 steps here. They have this vertex form they're going to be using, which is good. I like to first identify the vertex as, hk here, and then I'll just write the equation generically, as in, so far in this equation, we have this information. Okay, so kind of like that. And then I'll substitute my x, y, this known set of values afterward to say that ultimately what I'm trying to do is basically find my a. But I'll temporarily plug in 0 for x, 15 for y, which is what they do. And they're using this algebraically solving for a. They subtract 35 from both sides. They do 0 minus 50 and square it to get 2500. Then they divide by 2500 to get this decimal. That becomes the a value in their model. They never did write the model. Oh, here it is. They wrote the model straight up right here. And that's their stretch factor. Now, before I move on, let me show you a way that I would do it, I could do it, which is basically like this. You know our whole 1, 1, 2, 4, 3, 9 kind of setup? Yeah? Well, if we flip it over, it's still 1, 1, 2, 4, 3, 9, unless a new stretch factor is applied to it. So, instead of 1, 1, I'm doing 1 this. Instead of 2, 4, I'm doing this, 3, 9. And instead of, I'm going from 50 to 0. Instead of going over 50 and going down 50 squared, right? Instead of going over 50 and going down 2,500, I'm going over 50 and down from 35 to 15. I'm going down 20. So I'm multiplying 2,500 by some stretch factor, and I'm going down 20. Doesn't that look like this step right here? It does, right? So that's the same setup. Instead of plugging all that stuff in to get there, I can also get there in that way. Sometimes it's really easy to figure out what it is. Instead of going up 9, I'm going up 18. A is clearly 2. Anyway, I'm going to keep moving on with the problem. If you want to see me do that later, I can. Now they're going to say, all right, the x value is 90 at some point, right? There's some 90 comma something. And what is that something? We'll plug it into your equation. When x is 90, do the work, you'll get about 22.2. So the height of the net's around 22 feet. So it's just about, modeling with quadratic data. Same thing we did with linear, only we have to do something specific to get the quadratic equation. Let's write an equation using a point and x-intercepts instead. Let me cover this guy right there. All right. This time we're given the two x-intercepts 4 and 24. We're given another random point that's 0, 9.6. It's not 0, 10. I assumed it was, but it's not. So we can plug them into this equation in the same way we did before. We have an x-intercept of 4, plug it in. An x-intercept of 24, plug it in. And if you want to write it bluntly like that to start with before plugging in x and y, go ahead. Otherwise, you have an x, y value right here. This is a solution to your equation. 0, 9.6, plug in 0 for x, 9.6 for y. Your goal is to solve for a. So you do the work, right? Clean the stuff up. You divide both sides by 96. Apparently get 0.1 for a. So now our equation is modeled like this. This is for the entirety of the graph. Now, was there another question with it? Let's see. I didn't actually read the question. A meteorologist creates a parabola to predict the temperature tomorrow, where x is the number of hours after midnight. So here's midnight. And then as the day goes on, really, why does it get cooler regularly? Okay. And y is the temperature in degrees Celsius. Write a function f that models the temperature over the time. What is the coldest temperature? So in order to get the coldest temperature, right, we're going to have to first get an equation and then find its vertex. So we came up with the equation, boom. Now we're going to find its vertex. So what they're going to do is if the x-intercepts are 4 and 24, I don't know if you needed, you did need the equation because you have to plug it in to find y. But you're going to average 4 and 24, which is 14. That's halfway between 4 and 24. Then plug 14 into your equation from your model. You plug 14 in, apparently you get negative 10. The coldest temperature is negative 10 degrees Celsius at 14 hours after midnight or 2 p.m. Why is it colder in the day and warmer at midnight? I don't know. Anyway, this meteorologist having trouble, I believe. What is the average rate of change in temperature over the interval in which the temperature is decreasing and increasing? Compare the rates of change. So, average rate of change is another way of saying slope, the slope between 2 points. So we're going to find in which the temperature is decreasing and increasing. From here to here, the temperature is decreasing that entire time. I want to find the average rate of change between those 2 points. Means I want to find its slope. I want to find that rise over run or fall over run. How much down, how much over. It's pretty much that. y2 minus y1 over x2 minus x1. Count the distances between, anything like that you want to do the division. That's all it means when they say our average rate of change. That's the average rate of change of decrease, and average rate of change of increase is from here to here. What's the rise over run from there to there? So they're going to do the same. Oh, they drew the exact same thing. I thought they were just going to show the math on it. So they're going to do the exact same thing, right? What's the fall from 9.6 to negative 10? Well, that's 19.6, negative 19.6. What's the run from 0 to 14? Well, it's 14, and you divide those and you get negative 1.4. It falls 1.4 degrees Celsius every hour, is what they're saying. On average, right? It's actually a parabolic rate, but that's the average rate of change that they're doing from there to there. And then the average rate of change from here, it rises 10, and it runs 10. So that average rate of change is 1 degree Celsius per hour on average. And was there another question with it? Oh, compare the average rates of change. So in comparing them, this has a greater fall than this has a rise, basically. It's getting colder faster on average from this duration than it does from this duration here. But of course, it's a parabola. It's symmetrical. So if I kept going another 14 hours, then it would be a tie. But they say because the absolute value of negative 1.4 is greater than the absolute value of 1, the average rate which the temperature decreases from midnight to 2 is greater than the average rate which it increases from 2 to midnight. Oh, that does go to midnight. I take it back. Okay. All right. I still don't know why it's coldest midday. I have no idea. I don't know where that is. All right, writing equations to model data. When data have equally spaced inputs, you can analyze patterns in the differences of the outputs to determine what type of function can be used to model the data. Linear data have constant first differences. Quadratic data have constant second differences. Yeah, I can't remember when I last did a recording with the things on differences. I want to say it was probably chapter 5 of IM2, the IM2 book. We might not have done it since then. So if we haven't, what they're saying here is, if you're going, 2, 4, 6, 8, 10, if the y values increase by 2 each time like that, that's clearly a linear difference. But if it goes 2, 6, 12, 20, 30, like that, and it's jumping more and more, and those differences have a common difference, clearly we're going to find one with an example like that. That'll be a quadratic. So we're going to look at those. So here's an example, writing a quadratic equation using 3 points. So first we have to identify something as quadratic. NASA can create a weightless environment by flying a plane in parabolic paths. Yeah, you can have I think it's called parabolic free fall or something like that. Oh, no, parabolic dive, where you feel like you're just floating. It's cool. Look it up. That's how they shot Tom Cruise's The Mummy. There's a scene where they do that. They do a bunch of parabolic dives to make it look like they're in free fall. It's not CGI. Or wiring. The table shows heights in feet, h in feet, of a plane t seconds after starting the flight path. So here's time as it goes on. Here's the plane's height. It looks like it goes up, hits some peak, and then it goes down again. Passengers experience a weightless environment above 30,800 feet. Write and solve an equation to approximate the period of weightlessness. So anything above 30,800 feet is that. So we have to find out how much time is there. So there's a lot of things we got to do in this problem, actually. Quite a bit. First of all, with this data, we got to determine that it's quadratic. And so they're doing that here. They're showing the differences. These are constant. Do I say constant? Constant or consistent intervals of time every 5 seconds here. And then this is not a constant linear change. This is not a constant change in difference, right? Difference here is 21.25, 15.75, 10.25, etc. Then it goes negative. But the difference between each difference is constant. So from 21.25 to 15.75, you subtract 550. From here to here, you subtract 550. That is indicative of a quadratic function. The way they set it up is perfectly quadratic, so that means it's a quadratic function. How do you get your equation? You still got some more things to do. And to get this quadratic equation, we got to choose 3 points, because none of them are necessarily the vertex, and none of them clearly are x-intercepts. So we're going to have to do a standard form equation. So we have to choose 3 of these points, maybe 1, 2, 3. We have to choose 3 of these points and solve a system of 3 to get the a, b, and c of a quadratic equation. They're going to show you how to do that here. This is actually a really big problem as a whole. So yeah, they're choosing those 3 sets of points. 10 when time is 10 and 15 and 20. They're using these here. And they're basically taking the form y equals a, well, normally it would look like y equals ax squared plus bx plus c. And our goal is to find out what a, b, and c are in the equation by plugging x, y into that equation. We got an xy here, here, and here. So plug in 10 for x, a times 10 squared is 100a, b times 10 is 10b, then plus c equals the y value. Then this one, etc., etc. Now keep in mind, these are t. I said x and y. I really meant t and h of t, but you know what I mean. Those are the x's and y's. Set them up, and then we solve the system. You can use any method. You can use elimination, substitution, whatever. They're going to use elimination. It's best. You can cancel out your c's and then do a bunch of stuff with that. I'll probably reduce my numbers if we have to do something. This is a big problem, guys. This is a really big problem. Anyway, you do your solving system stuff as we did from section 2.4, and you get an a value of negative 11, a b of 700, and a c of 21,000, and this ends up being your model for that entire equation. Now, I'm sure we get to practice this a couple times. If you're not understanding it this first time, we'll progressively go through it as a whole on an actual problem. But now we got to find out what t range, what interval we're actually at a height of 30,800 or higher. So we got to find out what values of t. See, this is a parabola right now, right? We have a parabola that's doing this. And here's where time is 30,008, or here's where we have a 30,800 feet. We have to find out what time here to what time here we have it. So we have to solve for these values of t, this t here and this t there. So we're going to set this model equal to 30,800, and then we're going to solve for t. Apparently, you got to use quadratic formula. So let's go ahead and take a look. Quadratic formula is the whole x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So t, in this case, equals that, and I'll let it simplify itself. If we have to use quadratic formula, we will. This is a big problem. Anyway, so it goes from about 20.8 seconds, time 20.8 to time 42.8. That difference between those two is about 22 seconds of duration that you're in that parabolic freefall. So, again, Tom Cruise and stuff filming that movie, The Mummy, and do this. They only get about 22 seconds of footage and action. You get this time, they had to do it over and over again. I'm sure that was either very thrilling or very nauseating or very, I don't know, very time consuming and very expensive is a for sure. A lot of safety measures in play. Okay, so there's that one there, and they use standard form. So we're going to have to definitely practice a lot of standard form with that. And probably finally, real-life data shows that a quadratic relationship usually do not have constant second differences because the data are not exactly quadratic. Relationships that are approximately quadratic have second differences that are relatively close in value. Many technology tools have quadratic regression feature. If you recall, when we used the graphing calculator before for the linear regression feature, there was a quadratic regression feature that we didn't use because our points were not really quadratic in nature, they were linear. But now we're going to use it, it looks like. Okay, using quadratic regression. The table shows fuel efficiencies of a vehicle at different speeds, but it's not exactly quadratic, but it's probably quadratic-like. Write a function that models the data, use the model to approximate the optimal driving speed. So we have it all right here. We would enter this in our calculator, right? We'd use those lists. If you saw that in that one section that we did it, I think 2, 3. You saw what we did there. But we're not going to, here are the points as a graph. It looks very quadratic-esque, just not exact, I suppose. So we're going to use the quadratic regression feature, and it shows the stuff right here. Now, it doesn't have the correlation coefficient r, but it does have r squared, which says how much percent of the data is explained by, x and y relating together. So 99.9% of the data does. I'd say it's pretty close. So we can trust using these numbers. Now, they did have to do some rounding with these numbers here for A, B, and C. We're going to have to deal with it. I'll round as little as I need to, I suppose, or as significantly. Anyway, so there are the numbers. It says use the model to approximate the optimal driving speed. Now that we have this standard form equation, the optimal driving speed is where x, miles per hour, gets you the best miles per gallon rate. So at what speed gives you that? So we got to find out what the x value of the vertex will be. Now, we have the graphing calculator for this as well, right? We can use this and we can trace the maximum. I'll show you how to do that on a graphing calculator when we do our own problems, if that's the exact kind of question we have. But they're finding the vertex. They're finding what x value of the vertex does this. And I wish I could figure this out on my car as well. I think most cars are like 77 miles an hour or something like that, all depending if you're on the freeway. Anyway, so right here, the maximum speed would be 48.9 miles per hour. They say about 49 miles per hour. It gets you about 26.4 miles per gallon, apparently, but the question was, what's the x value of the vertex, really? So there is that. Oh, here's them explaining the r squared. The coefficient of determination, I didn't know that was the phrase. R squared shows how well an equation fits a set of data. The closer r squared is to 1, the better the fit. They don't actually state how it represents a specific percentage. It actually specifically represents a number that explains something. Anyway, all right, that is the lecture portion. Right around our 20-minute mark, let's go ahead and answer the vocabulary and core concept check questions. And then we'll do numbers 3 through 37, I think it was. Or was it 39? It was 37. Happy day. Okay. Number 1. Explain when it is appropriate to use a quadratic model for a set of data. Well, you have two different things. I'm going to answer it up here. You have two different things that we can look at. One is with the calculator. Calculator, when the data appears to form a parabola. But in a non-calculator setting, what we're doing is when the second differences are constant. Now, I'm stating it the way that they state it. The way that I kind of state it normally is when your common difference, or when your differences have a common difference. And that's kind of a weird way to say it, but that's kind of how I answer it. All right, different words, same question. Which is different? Find both answers. Excuse me, they're giving you a visual of a parabola, and they're showing this red line. That's one of those things, finding the slope. They call it average rate of change. Right here, what is the average rate of change over 0 to 2, the interval 0 to 2 on x? So that's one. What is the slope of the line segment is the same question. And it's good that they bring up this kind of thing because I want to remind you average rate of change is another way of saying slope. Now remember, parabolas themselves don't have slopes, but if you want to average it over time, you can. Parabolas have an instantaneous rate of change. At every single point, it has a very specific slope, but not one single slope over time. This has a constant slope over this time. What is the distance from f of 0 to f of 2? That's not the same. That is just saying what's the rise. What's the rise or the fall? So this is like going down to, that's the answer to that question, right? That negative 2. By the way, I didn't answer these questions here. This slope seems to be negative 1 because it's down 2, right 2. So that's a slope of negative 1, slope of negative 1. What is y2 minus y1 over x2 minus x1? The f of 2 minus f of 0 is the value of y1x is 2 minus the value of y1x is 0 over 2 minus 0, which is negative 2 over 2, which is negative 1. Oh, that's an A. So which is different? This guy is different. That's not a rate of change. That is just a change in y. All right, guys, we are going to go ahead and jump into the problems 3 through 37. This is the last section of chapter 2. I'm excited to get this started and finished for you guys, of course. Grab whatever you need. Calculators, graphs. It doesn't look like we're doing many graphs ourselves. All right, now, we did a lot of graphs in the previous section 2.6. It doesn't look like we're doing many graphs ourselves, but we are writing equations based off graphs. Numbers 3 through 8, write an equation of the parabola in vertex form. So on number 3, we have a vertex of negative 2, 6, and then we have some point, some xy value that's negative 1, 3. Now, in my way that I would generally do this is just this. We know our 1, 1, 2, 4 stuff. From negative 2 to 1 is going over 1, but instead of going up 1, we're going down 3. If we go up 1 and down 3, that seems like the A value is negative 3. We'll see if we get an A value of negative 3 based on what we do. Now keep in mind, this is our HK, this is an XY, but as far as our HK goes, currently our equation would look like y equals A times X minus H quantity squared plus K. Hopefully we're really good at vertex form and knowing that. And our goal is to find our A value. We're going to use this negative 1 for X and 3 for Y to find that. So we plug in 3 for Y, negative 1 for X, and let's solve for A. Subtract 6 from both sides. Negative 1 plus 2 is 1. 1 squared is 1, so negative 3 equals A. Well, I got A as negative 3 as well. That works out. So the final equation is going to be y equals, don't forget to reinsert y and x, negative 3 times x plus 2 quantity squared plus 6. Remember, the goal is to write the equation for the parabola, the entire thing, every x, y that goes with it. We just need to find the A that associates with the one that gets that solution given that vertex, and we just did. Number 4. Number 4, we have a vertex of 4, negative 1, and an xy point. Hopefully you now know that they are those kinds of points. An xy point that is 8, 3. Now when it comes to my, again, the equation right now would look like y equals A times x minus 4, quantity squared minus 1. I'm going based off the HK. We are going to plug in these xy values, but before we do, I want you to observe how I can do this kind of by hand. We're going from 4 to 8. That means we're going over 4. When we go over 4, normally we'd go up 16, right? 4 squared. But now we're going up 4. We're going up 4 instead of going up 16. That's like dividing 16 by 4, right? Or multiplying by 1/4. I'm expecting a value of 1/4 here. That's kind of a way you can go about that mentally. Some are going to be a little bit trickier. If instead of going up 16, I'm going up 2.8, we're going to talk about how we can kind of work that mathematically without having to plug these in. But I am going to plug these in. Let's plug in 3 for y, 8 for x, add 1 to both sides to solve for A as we do 8 minus 4 squared. 4 equals 16A. See, this is the step we can get to. Normally we'd go up 16, but now we're multiplying it by our stretch factor. Instead, we're only going up 4. So what is that A value? Divide by 16 to figure that out. 4 over 16 is 1/4. So that's where I got the A value of 1/4. That's where I got the A value of 1/4. The final answered equation is y equals 1/4 times x minus 4 quantity squared minus 1. There's our vertex form on 4. Numbers 5 through 8 are also the same kind of question, just no visual graph. So maybe it's harder for us to do the thing that I was saying before by looking at the numbers. Maybe we can still do it. Let's take a look. The vertex is 3, 2, and we pass through the point 13, 8. So again, as an equation right now, we're looking at x minus 3 quantity squared plus 2. Now, what a value do I predict? Well, we're going from 3 to 13 on x. That means we're going over 10. We're going over 10. Now, normally, in a standard, when I say normally, I mean when the stretch factor is 1. With stretch factor is 1, we would have got up 100, but now we're only going up 6, right? Instead of going up 100, we're multiplying it by a stretch factor, and now we're only going up 6. That is crazy small in comparison. So a is going to be 6 over 100, which is, it depends. You can either say 3 over 50, or you can say 0.06. Either or is going to apply, 3/50ths or 0.06. Now, I got to this 100a equals 6. I imagine we're also going to get to this 100a equals 6 as we do the problem through this method of plugging in this for x and this for y. So 8 equals a times 13 minus 3 quantity squared plus 2. Subtract 2 from both sides, we get 6. A is 10 squared, and 10 squared is 100. We get 6 equals 100a. Hey, we've been there before, right? So you can see where I'm getting to that stage. The difference between this y and this y, your k and your y value, is 6. From 2 to 8, that's our rise. The difference from 3 to 13 is 10. That's the thing that we're squaring. All those things are involved in what I'm doing there. I'm just giving them more of the visual representation from how we do graphs. Anyway, so our equation can either be y equals 3/50ths times x minus 3 quantity squared plus 2, or y equals 0.06 times x minus 3 quantity squared plus 2. I almost feel like wanting to do the first one, unless it's a word problem. I don't know why. Just depends on what we're doing with it. So either or works there. Number 6. Anyway, I think about these things when I do these videos, as far as like, do people care that I'm doing things 2 different ways? A way that I prefer is the way that you prefer. I mean, listen, these are my videos. I prefer to do what I like, and this is how I teach it. So it's those kinds of things. I'm trying to give you efficiency for it. So like, for example, here, let me give you this answer here, right? We're going over 2, and we're going down 24. Normally we'd go down 4, so this stretch factor must be -6. So I believe the final answer is going to be this. Now, would you be interested in doing that fast, like I did? Or would you rather plug it in with all this other stuff? Let's see. So let's plug in -15 for y. We're trying to find a. Let's plug in, see, I don't like to do this all in one step like this. -7 for x, and then +5 quantity squared plus 9. So we got that part. I'm going to subtract 9 over to get -24. -7 plus 5 is 2. 2 squared is 4, so -24 equals 4a. Divide both sides by 4, you get a equals -6. So yeah, I do prefer to write the original kind of this part of the equation, going like here it is with the vertex, so you know what you're reinserting and what you were trying to solve for along the way. Our goal is to solve for a. Now that we found it, we're going to place it right in there, and then we get, boom, our final answer here. So that is the final answer that I got still, though, right? -6 was my stretch factor. And how did I get that? Again, I went over 2 from -5 to 7. Doesn't matter if you go 2 right or 2 left. When you go over 2, we normally go up 4. Well, now we're going down 24. Down is negative. 24 is 6 times more than 4. That's where I got -6. And again, I keep re-explaining. So I'm going to do that for the next 2 problems, assuming that they are reasonable values to go mentally with. If not, I'll still do it the conventional way that you're used to. So we got a vertex of -6, -12. And we're passing through the point 0, -24. So we're going over 6, we're going down 12. Normally we go going down 12. Normally we go up 36, so the a is -1/3. So our equation is y is -1/3 times x plus 6 quantity squared minus 12. Okay, but let's go ahead and do it the other way. So our equation is to find that a with x plus 6 quantity squared minus 12, these being the vertex values. Let's plug in -24 for y, 0 for x. I think it's safe to say that 0 plus 6 squared is also 6 squared, which is 36. I'll save you a step. Add 12 to both sides, and you get -12 there. And then 36 divided from Negative 12 will reduce to negative 1/3. And that's our A value. And that leads us to our final answer there. So again, I don't know if you're impressed or not, but you make the decision on how you want to go about doing what you do there. Depends on the numbers. Remember, there are some times where I still have to write this out here. I said instead of going up 100, I was going up 6 or whatever the numbers were, right? Yeah. I still had to write that step. But I saved myself some steps along the way. All right, let's go to number 8. On number 8, we are passing, vertex is at negative 1, 14, and we're passing through the point 6, 35. We're going over 7, and we're going up 21. Normally we go up 49. This is an instance where I'm saying 49a equals 21, and I got to solve for that. A is 21 over 49, which reduces to 3/7. And this is the one where I'll leave a fraction as well. So I know the final answer here is going to be A times x minus h quantity squared plus k. All right. Now let's go ahead and do that the conventional way. Let's start with that A here. We know our x, or our h and k. Let's now plug in 35 for y, 6 for x. Subtract 14 over to get 21. 6 plus 1 is 7. 7 squared is 49, and you can see where we get that 21 equals 49a, which gets us to 49a is 21, and that thing right there. So we still have that final answer of 3/7 as we reduced it, and we are done. All right, those are 6 different vertex form questions. Let's move forward to numbers 9 through 14, where we're going to write them in intercept form, also known as, or what I also call, factored form. Now, factored form, you could probably do some of the same stuff that I was doing before, which is once you know your intercepts, work the stuff out. So we have, I don't know if I want to write the numbers or not. Okay, we have x, and yes, I'll do that. We have x-intercepts of 4, 0, and 2, 0. And we have a point that we're passing through that is 3, 4. Now, keep in mind as we're doing this stuff, this is our p and our q that we need in our equation. This is the x, y we'll be substituting later, so we can find a. To follow along with the patterns we were doing before, let me write this in the same way I was doing before. This is your vertex form, this is your intercept form that looks like this. This is x minus p times x minus q, like that. Our goal is to solve for a, and we're going to substitute this for x and this for y to find a. Now, if I were doing it in my graphing form, I'd still do the same stuff that I had if I have my vertex. Thing is, we're not often going to have vertex. I think this time we do, so I can luck out. I'm going from 3 to 4, which means I'm going over 1. Normally I'd go up 1, but now I'm going down 4. That means my a should be negative 4. A should be negative 4, but let's go ahead and plug in 3 and 4 to figure that out. So 4 equals a times 3 minus 4 times 3 minus 2. So 4 is a times negative 1 times positive 1. Negative 1 times positive 1 is negative 1. 4 is negative a, so a is negative 4. And that's the value you saw above. I think I lucked out with this one because we had the vertex. Often we won't have the vertex, so I can't do my graphing thing that I normally do. You're going to see a lot more work like this. Anyway, so the final equation is going to be y equals negative 4 times x minus 4 times x minus 2. And that's the factored form version of this problem. Okay, let's go to number 10, also with the graph. And you can see on number 10, we do not have the vertex written out this time. So I don't dare kind of work out that stretch factor stuff. I'm just going to do it in kind of these conventional ways now. So the x-intercept is, or x-intercepts are, negative 1, 0, and 2, 0. So, and there's a point we're going through that's 1, negative 2. That'll be our xy. So we got an equation that's looking like y equals a times x plus 1 times x minus 2. We plug in negative 2 for y, 1 for x. And I think after this problem, I'm going to do these calculations kind of like 1 plus 1 is 2. I'm going to write 2, and 1 minus 2 is negative. You know what I mean? I'm going to do them a little faster. So 2 times negative 1, because you can see where this is like extra work. So the a value is 1. So if the a value is 1, we can write our equation kind of without a in sight. We can just do x plus 1 times x minus 2, and that'd be good. Apparently, that's our stretch factor. Didn't know that. Now I do. But apparently, that's our stretch factor for number 10. All right, number 11. No graph. Let's pull out the information regardless. X-intercepts are, I'll just write it this way, 12 and negative 6. The point is 14, 4. Okay, so our equation can look like a times x minus 12 times x plus 6. Okay, let's plug in 4 for y, 14 for x. 14 minus 12 is 2, 14 plus 6 is 20. So we get 4 equals 40a, and therefore a is 4 over 40, which is 1/10, or 0.1. I'm going to leave it as 1/10. So our final equation is y equals 1/10 times x minus 12 times x plus 6. All right. Okay, let's go to number 12. A lot of drill and kill. A lot of drill and kill. A lot of practice. Can't be wrong after you do it so many times. Maybe they'll throw a trick up your sleeve. X-intercepts are 9 and 1. The point is 0, negative 18. Also a y-intercept. Our equation's looking like a times x minus 9 times x minus 1. Let's substitute negative 18 for y and 0 for x. That's negative 9 times negative 1, which is positive 9. And a is negative 2 when you divide by that. So our final equation can be y equals negative 2 times x minus 9 times x minus 1. Yeah, definitely something we did in IM2, probably to this extent as well. So I don't know what section it was at IM2. 3.4, something like that. I don't know. Something where it's called intercept form. X-intercepts are negative 16, big number, and negative 2. Oh, also big numbers. Negative 18 and 72 are the xy points. Let's try and plug them in straight up this time. 72 goes in for y. Negative 18 goes in for x. Oh, what's negative 18? Now, see, this is where you have to be careful. Negative 18, I'll write this out, plus 16, and then negative 18 plus 2. Maybe I didn't really save a step anymore by doing that. 72 equals a. I prefer my other method. Negative 2 times negative 16, which is positive 32. So not totally clean. Not totally clean here. 72 over 32, it can reduce. They can divide by at least 8. 9 over 4. 2.25. So y equals 9/4 times, that kind of looks like 9/9. 9/4 times x plus 16 times x plus 2. You can probably see I was trying to fish for the thing where I wrote an x before. Yeah, I totally prefer the methods where I write the y's and x's, you know, kind of beforehand. I think it just makes me feel a little bit better about what's there. Anyway, you could also write it as 2.25, depending on what you want to do there. But 9/4, that works for me. Okay, let's go to number 14. Probably the last one of this set, where we have x-intercepts of negative 7 and negative 3. Well, I wrote a negative 3 first for some reason. And it passes through the point 2.05. Okay? So let's get to that first part. Y equals a times x plus 3 times x plus 7. 0.05 goes in for y. Negative 2 plus 3 is 1. Negative 2 plus 7 is 5. So we got to divide this by 5, right? A is 0.05 over 5, which is 0.01. Or 1/100th, but because this started as a decimal, I'll leave it as a decimal. So 0.01 times x plus 3 times x plus 7. You might have written the x plus 7 first because you probably copied the problem down correctly, or as they had it written. All right, let's keep moving forward. Let's look at number 15 on writing. Explain when to use intercept form and when to use vertex form when writing an equation of a parabola. Well, they stated it in the very first part of their lecture. Use vertex form when given, write it in vertex form when given the vertex and a point. Now, technically, we could have used vertex form on this number 9, right? Number 9, we could have said, given this vertex and a point, we could have done vertex form. They just forced it on us. Or when requested, or upon request. No, that's a joke. Use intercept form or factored form when given x-intercepts, the x-intercepts, and another point. So yeah, that was the same part as the beginning of our lecture portion as well. All right, number 16. Analyzing equations. Which of the following equations represent the parabola? Now we have, here's the thing, they give us the vertex, they give us the intercepts, so they're probably saying, hey, use both forms. This is kind of like that number, whatever I said before that just had it. We'll use both of those, and there's probably more than one answer. Which of the following equations? So let's do both. Let's treat it like vertex form, where we're given the vertex, which is 0.5, negative 4.5. And here's the thing. I don't think the book trusts us yet to be able to do like completing the square to get in vertex form. Actually, they should. We just had to do it in the last section. Or factor. We should be able to factor as well. I don't know. But you can go from one to the other if you truly wanted to. But let's do it based off what we've been practicing. Let's choose a point on here. We can either choose negative 1, 0 or 2, 0. The point is you just got to choose one of them. I'll choose 2, 0. I'll stick with another positive number if I can. I'm not going to do my other method right now. I'll just go off of theirs. So let's do y equals a times x minus h, quantity squared, plus k. Let's substitute 0 for y, 2 for x. Add 4.5 over. 2 minus 0.5 is 1.5. 1.5 squared is 2.25. And, whoops, let's write 2.25a. And 4.5 divided by 2.25 is 2. So a is 2. Therefore, the equation that we can write in vertex form is y equals, this is vertex form, is y equals 2 times x minus 0.5 quantity squared minus 4.5. So there's one of them. Which one does that match up with? C. So C is one of them. And honestly, I could have found, oh, here's the thing. We probably don't have to do all this extra work. I probably should have looked at these here, guys. I'm sorry. Okay, now that I have that one, I'm not going to do the extra work for the factored form. But the point is we can use both, right? We can use the vertex there. Now we can use these as x-intercepts with this as the third point. But now that we're just looking at these things, I probably should have noticed it's not going to be B because B has a plus. You're probably screaming at the screen saying, go use that. So it's not going to be B. Now, the stretch factor is 2 on each of them. So the question is this x minus 2 and x plus 1 or x plus 2 and x minus 1? It's actually this one, A. So the other answer is A. Like I said, I'm not going to go deep in there to solve for A. We've already done a lot of problems with that. So go check those ones out if you can. But here's the other one, like that. Okay. Yeah, totally should have looked at the options first. My bad. Okay, let's go to exercises 17 to 20, where we write an equation of the parabola in vertex form or intercept form. So they're really going off of this number 15 and saying, make a choice based on what you have. Make a choice based on what you have. And maybe you get more than one option. So on number 17, we're given those 2 points as a for sure. It looks like that's your vertex. Does it look like it hits? It might hit 6, 0. It might hit 0, 0. I don't know that as a for sure, so I'm just going to go based off of these. Now, if I were to go my route, you know what I'm talking about? We're going over 2 from 3 to 1, right? We're going over 2. Instead of over 2 up 4, we're going over 2 and down 64. 4 times what is 64? 16. So my A value is negative 16. This equation is going to be y equals negative 16 times x minus 3 quantity squared plus 150. But you're not here for that. You're probably here, or maybe you are. You're probably there for that quick impression of what to do, but now let's go ahead and do it the conventional way. We will use vertex form, and let's use the vertex. X minus 3 quantity squared plus 150. And let's substitute. This is through the point 186. Your vertex was, by the way, 3, 150. So let's substitute 86 for y. 1 for x. 1 minus 3 is negative 2. Subtract 150 over here, you get negative 64. Negative 2 quantity squared is 4, so you get 4a. Divide both sides by 4, you get a is negative 16. This is where we're getting that number there. All right, that's number 17. Let's go to number 18. Now, given that they're saying use vertex form or intercept form, based on the visual here, we're going to have to make the assumption that's the top part, which is the vertex. vertex is going to be at 0, 180, and the point we're going through is 1, 164. We're going from 0 to 1. You're going over 1. Instead of going up 1, we're going down 16. That sounds like an a value of negative 16, which means my final answer will be, wasn't it negative 16 last time? Oh, and x minus h is just x here. It's just x squared plus 180. I believe this is going to be our answer. Under that belief, let's go ahead and do it with this other format. Y equals a times x minus 0 quantity squared plus 180. Understand x minus 0 is the same thing as x. So when I substitute 1 for x, it'll just look like a times 1 squared. And 164 goes in for y. Subtract 180, you get negative 16. And a is negative 16. 1 squared is 1. I got rid of that part. And I got rid of the x minus 0 and turned it into just x squared there. Oh, this was number 18. Sorry, didn't move it over. They didn't ask us to interpret these things. This is flare signal, height and time. So they didn't ask us to interpret anything here. So I'm just going to leave that. All right, let's go to number 19. On number 19, we don't have a vertex, but we do appear to have the intercept. So we're totally going to use intercept form here. So we have x-intercepts of 0 and 4. We have a point that we go through that is 3, 2.25. I'm going to work off of this. Looks like this is the vertex though at 2, 3. If I had to guess, we're going from 2 to 4 and we're going over 3 to negative 3. Shoot, now I just messed up. Is that negative 3/4? Is a negative 3/4? Let's find out if a is negative 3/4. Anyway, y is going to be a times x minus 0. That's just x, right? Times x minus 4. So 2.25 goes in for y. This is a times x, 3, times 3 minus 4 is negative 1. So 2.25 equals negative 3a. Divide by that, you get a is 2.25 over negative 3. Oh, we don't dare leave that like that. I believe that's negative 0.75 because 2.25 is 3/4. Yeah. Negative. So negative 3/4. Negative 3/4. So that's the a value. I think that's what I said it was going to be. So we're going to get y equals negative 3/4 times x minus 4. And here's probably the way you'd see it written on an answer key as well, right? They wouldn't put x in parentheses. They wouldn't put x minus 0. It would just be outside. It would be attached at the hip with that. That's the best way you can see that, recognize that is intercept form. Number 20 looks like we're going back to vertex form again. Ooh, that's weird. So we got a vertex. I wonder if even going about it my way is going to work out like here. But no matter what, you got some interesting calculations. So on number 20, we got a vertex of 3, 1. You do, I think you have an x-intercept of 0, 0. And you could get the other x-intercept here. Here, let me talk about this for a second. If this is truly 0, 0, which it looks like it is, 3, 1, 3 is the x value there, so another 3 over would be 6. So you could choose 6, 0 as the other point, and you could use intercept form either with these 2 points and that point, or these 2 points and that point. So you could use it. No one's stopping you. I'm going to go ahead and use vertex form, though, based on not being certain that that's at 0, 0. I am all but certain, but we're not going to use it. Anyway, from 3 to 1, we're going over 2. So instead of going down 4, you're going down 4/9. Well, that sounds like your a value is negative 1/9. Instead of going up 4, you're going down 4/9. So it sounds like your a value is negative 1/9. I'm going to guess we're doing this. So let's take a look and see if that's going to be it. So y equals a times x minus 3 quantity squared plus 1. 5/9 is the y value. We have 1 minus 3 quantity squared plus 1 here. I got to subtract 1 from 5/9. 1 is 9/9, so 5/9 minus 9/9 is negative 4/9. And you have negative 2 quantity squared there. Excuse me, correct answer. We're playing this 4a. Now we're going to divide both sides by 4. Dividing by 4 is also multiplying by 1/4, if that helps you on this side. Negative 4 over 4 is negative 1, so you're left with negative 1/9 there. So a is negative 1/9, which is what we have here. And there's our final answer. That's vertex form. If you're interested in intercept form, because a is still negative 1/9, I can write that answer for you, assuming that that x-intercept is 0 and the other x-intercept is 6. It's probably that answer there. So I'm going to provide you that one because it's possible that you went about it that way. You know what I mean? So we'll go and leave it like that. Okay, let's move on to number 21, error analysis. Describe and correct the error in writing an equation of the parabola. So they went for intercept form. Okay, I can see it. They have -1 and +2 instead of the other way around. So when using intercept form, the factors x minus p, the factors x minus p and x minus q resemble opposite signs, or display opposite signs from the intercepts themselves. They have x minus 1 and x plus 2 when they should have x plus 1 and x minus 2. Now, they never show the x part, or with x's and those numbers. They plug in 3 already, and they properly plugged in 3, and I'm sure they calculated everything right. But we got to fix this, and our equation's going to have x plus 1 and x minus 2 as the intercepts, and we're going through the point. We're going through the point 3, 4, so I'll plug in 4 for y as they did. I'll plug in 3 for x as they did, but we're doing plus 1 and minus 2. And it's not too much that's going to change, but it is going to change. So 4 times 1, which is 4. 4 equals 4a, so a equals 1. So if a equals 1, then the equation is going to be 1 times x plus 1 times x minus 2. That's the final answer. All right, there's the correction to number 21. Let's go to number 22. Mathematical connection. The area of a rectangle is modeled by the graph where y is the area in square meters. So y is represented as area, and x is the width in meters. Okay? Rectangle, they said? Yeah. Write an equation of the parabola. Find the dimensions and corresponding area. Of one possible rectangle. What dimensions result in the maximum area? Well, what we talked about is the squarer the rectangle, like if it's a square, the maximum area. I don't know if that's what they're referring to here. But they do have a graph. We have to write an equation for the graph. In writing the equation for the graph, we'll then have to find the vertex for it to maximize width, yada, yada. Anyway, we have x-intercepts on number 22 of 0 and 7. We have a point that we go through that is 1, 6. Due to that nature, we know that we have a times x minus 7. I want to really make sure you're understanding how that's working. It looks weird, but it works like that. 6 is a times 1 minus 7, which is negative 6. I'm really going faster on that, so our a value is negative 1. That's the stretch factor of this equation. So our equation in factored form looks like negative x times x minus 7. Also still very strange. Now, we still needed that information to find the vertex, despite the fact I could have used the graph or the just the understanding of half the distance between 0 and 7 to find the axis of symmetry. Your x-intercepts are 0 and 7. So the axis of symmetry is at x equals 3.5. But we need this equation to substitute in 3.5 for x to find the vertex, the y value of the vertex. Did they ask for maximum area? Oh, they didn't ask for maximum area. I probably jumped the gun a little bit. Oh, yeah, of course. Oh, write an equation of the parabola. I guess we did have to do that. Anyway, I'm going to keep moving on. So we have, I think that's 12.25. 12.25. So the maximum area occurs when you have a width of 3.5 meters. So let's see. Find the dimensions and corresponding area of one possible rectangle. What dimensions result in maximum area? So for us, you obtain a maximum area of 12.25 square meters with, I'll fix that in a second, by having a width of 3.5 meters and a length of, guess what, that would also be 3.5 meters. I'm not sure if you noticed or if you know, because I didn't simplify it, but 3.5 minus 7 is negative 3.5. So right here, this would have been negative 3.5 times negative 3.5. I guess we have to ignore the negatives for a moment. The fact is we're multiplying 3.5 by 3.5. X represents width right there. So length would also, be 3.5 in that case. So both of those would be 3.5 by 3.5. That's what we'd get for that. They said find the dimensions and corresponding area of one possible rectangle. I think they're referring to this one here. They're saying, which I should probably answer that as a beforehand or after or whatever, another possible area just based on this is 6 square meters when the width is 1 meter. Right? That's kind of what they're telling you on that part right there, that when the width is 1, you get an area of 6. That's not calculating anything, that's looking at the point. Okay, let's go to number 23 on modeling with mathematics. Every rope has a safe working load. Thank goodness. A rope should not be used to lift a weight greater than its safe working load. The table shows the safe working loads S in pounds for ropes with circumference C in inches. Write an equation for the safe working load for a rope. Find the safe working load for a rope that has a circumference of 10 inches. So once we have our model for our equation, we can plug in the circumference of 10 and get the safe working load based off that. What we want to do is determine what kind of equation this is. This might be the standard form kinds that we're doing now. Like from 0 to 180, that different, let me copy this over. But from 0 to 180, that difference is 180. From 180 to 720, that's not the same difference. And so it's not a linear relationship we have here. The question is it quadratic? And if it's quadratic, can we then get an equation off of that? It's very possible that 0, 0 is the vertex of this, and then the domain just goes from 0. But we might have to work a little beyond that. So this is a difference of 180, this is a difference of 540, and this is a difference of 900. Now the difference between 180 and 540 is 360. The difference between 540 and 900 is 360. Because they have a constant second difference, this is a quadratic equation. And because it's a quadratic equation, we can then make a quadratic equation based off that. The question is this the vertex? I don't have a true answer to that. I wonder if this is the start of standard form questions. Let me move forward and see. Yeah, they're probably doing the standard form ones now. I think that's what they want us to assume. After all, this is only one x-intercept. But if I were to venture a guess, it's possible that this is an a value of 180. It might just be this might be y equals 180x squared. But it also might not be. I don't know. Is that it? It depends. Is this the vertex? I don't know. Because I don't know, we're going to have to do this in a different way. What we're going to have to do is choose 3 of these 4 sets of points. This xy, this xy, and this xy will do for me. I'd love to choose 0, 0 as a point. That'll clean a lot of things up. Choose these 3. Whoops, 720. We're going to have to come up with, now I'm going to write the letters y and x. I know they have c and s, but I'm going to write the letters y and x here for a second. We're going to use the equation y equals ax squared plus bx plus c. We're going to find out what the a, b, and c are given these x, y's, write a system of 3, and solve that in standard form. So when I plug in, I'm going to do this one first. When I plug in 0 for x, I'm going to get a times 0 squared plus b times 0 plus c equals y, which is 0. That's awesome. I already know what c is in this thing. That's why I like choosing that point. When I plug in 1 for x, let's do it over here. When I plug in 1 for x, I'm going to get a times 1 squared, a, plus b times 1, b, plus c equals 180. And then when I plug in 2 for x and 720 for y, I'm going to get 2 squared times a, 4a, plus b times 2, 2b, plus c equals 720. So this is my system of 3 that I can use to solve for a, b, and c. Now c is already solved for. C is 0. That means I can work off this system straight up right here where I have 4a, well, I have a plus b equals 180, and 4a plus 2b equals 720. Okay, So with that in mind, I'm going to shift this over a little bit. I'm guessing this is the equation, by the way, because this said c was 0. If c is 0, then it's very possible that we have a... That's not necessarily true. Ignore what I said. I don't know what's right there yet. Let's eliminate b. Let's multiply top and bottom by, or let's multiply left and right by -2. We'll get -2a minus 2b equals -360. So we're going to getting to the bottom of the page is what I'm going to get. 2a equals 360, so a equals 180. I saw that number before. To solve for b, 180 plus b equals 180, so b equals 0. So yes, indeed the equation y equals ax squared plus bx plus c is going to be y equals 180 x squared plus 0x plus 0. So there's the equation we're basing this off of. So it is a simple quadratic equation like that so far. That means the vertex is 0, 0. Now, this is also, remember, S is our y and C is our x. Whoops. S is our y and C is our x. They're saying, find the safe working load for a rope that has a circumference of 10 inches. So what I'm going to do is substitute 10 for x, the circumference, and get the safe working load for that in pounds. 10 squared is 100. 100 times 180 is 18,000. So 18,000 pounds is a safe working load for a 10-inch circumference rope. Seems like a pretty big rope, and it's good that it can hold that amount, which is what I'm going for at least. That's the answer. I should put LBS rather. Okay, that's number 23. Let's go. Let's go to number 24. Still modeling with mathematics, I say. A baseball is thrown up in the air. The table shows the heights, y, and feet of the baseball after x seconds. Write and solve an equation to determine how long the ball is above 10 feet. How long is the ball in the air? Once again, we're seeing a representation of what's likely a quadratic equation. In fact, it's so much so that we see symmetry right here. It goes 6 to 22 and 22 to 6, and in between we hit a 3, which is likely the vertex. But I don't know the a value with that. I don't know the stretch factor because I'm not off the vertex, and we don't have intercepts. We don't have values of x and y equals 0. Therefore, we got to use standard form, but this is totally a quadratic equation by nature, right? If we're not sure of that, what can we do? See if the common difference has a common difference. Well, it's not necessarily totally a quadratic equation, but because we're in the section and because it goes up and down, then clearly it's supposed to be a quadratic equation. But let's go ahead and make that look kind of normal. And then we'll determine the difference here. We're adding 16, and then we're adding 0, and then we're subtracting 16. What the heck? Well, all of these have a what's 16 to 0 is minus 16, 0 to negative 16 is minus 16. So because the constants, the difference has a constant difference, this is a quadratic equation. Let's choose 3 of these points. 1, 2, 3. I'm choosing the 3 smallest points among these that I can use. So when x is 0, y is 6. When x is 2, y is 22. When x is 6, y is 6. So let's go 0 squared. Well, hold on. Y equals ax squared plus bx plus c. We're going 0 squared times a is 0 plus b times 0 is 0 plus c equals 6. There's our y-intercept. We'll get to plug that in a second. The second equation, let's do this 2's. 2 squared 4a plus b times 2, 2b plus c, which we know is 6 now, is 22. And now plug 6 into here. 6 squared is 36, so 36a, plus then we get 6b plus c equals also 6, like that. Now that we know c is 6, we can use that to substitute in for c right here and right here. And let's make that system of equations work. If this is 6, I can subtract it over and get 16. So I can get 4a plus 2b equals 16. And over here, if c is 6, 6 minus 6 is 0, so we get 36a plus 6b equals 0. Now I'm very intent on making these even smaller than they are right now. I can divide all these things here by 2 and get 2a plus b equals 8. You've seen me do that a lot before. 2a plus b equals 8. And over here I can divide these both by 6. And here I can get 6a plus b equals 0. All right, if I turn these into subtraction here, negative 2a minus b is negative 8, then we can combine these guys. 6a minus 2a is 4a. These cancel, and you get negative 8, so a is negative 2. A is negative 2. We can plug it into any of these equations to find b, even the 2a plus b. So that's negative 4 plus b equals 8. Add 4 to both sides, you get b equals 12. I'm doing systems of 3 a little faster than I used to because we did so many of them at the time, and this is just within one word problem. So now we have an equation, y equals ax squared plus b, bx plus c. That's our equation we're going to use for this thing. Y is the height of the ball, x is the amount of time. So solve an equation to determine how long the ball is above 10 feet. I want to figure out for what values of x do we actually hit 10 feet, because it's an upside down facing graph, right? So negative 2x squared plus 12x plus 6. Let's see when that actually equals 10. It should hit twice. It should hit on the way up and on the way down. And I want to find the interval in between here and here, how long it's actually above 10 feet. So I'm going to do this. I'm going to subtract 10 from both sides, and I'm going to attempt to solve this quadratic by any means necessary. First, by dividing everything by negative 2 to get x squared minus 6x plus 2 equals 0. Okay, I'd prefer solving by completing the square personally, so I'm going to subtract that 2 back over and get x squared minus 6x plus this unknown equals negative 2 plus that unknown. That unknown's 9 if you divide negative 6 by 2 and square it. Completing the square goes here and here. So this factors to x minus 3 quantity squared equals 7. And I can take the square root of both sides here. I apologize if I'm going quick on this portion. This is something done from IM3. This is something within the context of the problem that goes a little bit beyond what we've really been talking about. Not beyond, but we're solving quadratics. X equals 3 plus or minus root 7. Now, 3 plus root 7 is some number, 3 minus root 7 is some number, and we actually have to find the difference between the two. So I'd rather not round early. I'd just try to figure out the time that we're 10 feet in the air or more, above 10 feet, is going to be 3 plus root 7 minus 3 minus root 7. Now, I'm going to do this kind of by hand first. This becomes 3 plus root 7 minus 3 plus root 7 when you distribute the negative. The 3's cancel, and you end up with 2 root 7. Now, what is 2 root 7? That's where I'm going to use the calculator. 2 root 7 is around 5.29 seconds. Maybe 5.3 if the book does to the nearest tenth or something like that. So that's how long the ball is above 10 feet. It actually says how long's the ball in the air. I didn't answer that part yet. So time above 10 feet. How long's the ball in the air? That is when you set height equal to 0 and you solve for x. So I have the same equation right here. I want to set this one equal to 0. Negative 2x squared plus 12x plus 6. So negative 2x squared plus 12x plus 6. When is this equal 0? I still want to divide this by negative 2. Get x squared minus 6x minus 3 equals 0. Also not factorable. Also want to solve by completing the square. I'll make it fast this time. The plus 9. Add the 3 over, and we're adding 9 over there. So x minus 3 quantity squared again equals 12. X minus 3 equal, take the square root of both sides. Square root of 12, listen, I could either keep it like that, the idea is we're going to be using a calculator anyway, but I can put 2 root 3 as that. So x equals 3 plus or minus 2 root 3. So how long's the ball in the air? You go 3 plus or minus 2 root 3. Now here's the thing. 3 minus 2 root 3, and I'm going to do that in my calculator right now. 3 minus 2 root 3, I believe, is a negative number. It is. It's a negative number. Here's the idea. The baseball was thrown in the air. So when you think about what this thing is doing, and we have our standard form. We have this. The ball was thrown at 6 feet in the air to start with. The y-intercept is 6. That means it was thrown, it hits a peak, and it goes and hits the ground. This right here is 3 minus 2 root 3. This number means nothing to us. Anything on this side of 6 is diddly squat to us. Nothing, 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 nothing. All we really care about is the 3 plus 2 root 3. From time 0 to time 3 plus 2 root 3 is all that matters. I probably shouldn't be using red for that. Here's 0, and here's 3 plus 2 root 3. So my answer will be 3 plus 2 root 3. 3 plus 2 root 3 is, I don't know, let's see, 6.464, so around 6.46 seconds. Around 6.46 seconds in the air is the ball. That was a terribly stated sentence. But that's what we're doing with the ball for that question. Hopefully that's kind of making some sense there. So we said around 5.3 seconds here, around 6.5 seconds there. And we had the model. So solving standard form, you can see it was a robust problem. There was a lot of things that were asked. That's why I didn't want to spend a lot of time on solving the systems. We just did that stuff. Solving quadratics, we've done that in IM2. We'll probably do it a lot moving forward. Okay, number 25. Comparing methods. Gone an hour and 12. You use a system with 3 variables to find the equation of a parabola that passes through these points here. Your friend uses intercept form to find the equation. Whose method is easier? Justify your answer. They didn't ask us to solve. I don't know if we're required to solve. I kind of don't want to solve. I would use intercept form. I'd say your friend's method, my friend's method appears easier as it appears possible and requires less work. I have both intercepts, both x-intercepts at -8 and 1. And that should save time versus using standard form for 3 points. See, that standard form stuff, I don't know if I want to, I'm not going to do the whole thing at all, but the standard form stuff does what we just had to do before. We have to do -8 squared plus -8 times b plus c equals 0. And then 2 squared plus 2 times b plus c equals -20. And then 1 squared plus b plus c equals, we'd have to solve the system. I'd have to solve that system. You saw how factored form or intercept form ones work. I think that's, this looks to me in the system like more work. That's how we spell more work. Exactly. I'm not really digging that. So my friend's thing looks easier. Justify is just my explanation. I'm not going to actually do them, though. Okay, number 26. The table shows the distances, y, that a motorcyclist is home after X hours. Now, this one, guys, don't be fooled. When I look at this, I'm seeing a linear relation. In fact, that's what they're asking. Part A, I see a linear relationship in this thing. I see a constant change on X, and meanwhile, I see a constant change on Y. We're adding 45 each time the X increases by 1. So, to answer their first question, determine what type of function you can use to model the data. Explain your reasoning. Well, as X increases by 1 here, constantly, Y is increasing by 45. It appears linear, not quadratic. So part A, linear. You have a constant first difference is what we call that. Sometimes I just say common difference. Okay, part B. Write and evaluate a function to determine the distance the motorcyclist is from home after 6 hours. Well, the equation is going to be y equals 45x. The slope is 45, up 45 over 1. The y-intercept is 0. So y equals 45x. 6 hours, you plug in 45 times 6. If only each problem were this easy, we'd get 270 miles from home. Yeah, motorcyclist traveling at a constant rate, 45 miles an hour. Looks good. All right, quick question. Number 27, probably a long question now. Whoa, yep. They gave us an easy one, and they're like, all right, I'm just getting warmed up. All right, hopefully we have the room here. Number 27. The table shows the heights in feet, h in feet of a sponge t seconds after it was dropped by a window cleaner on top of a skyscraper. So, that's probably a gravity thing, so it's probably going to be speeding up as it goes. And my guess is we're going to get a -16. Well, it's a sponge. We'll see. I wonder if we're going to get a -16 t squared kind of thing for gravity. Use a graphing calculator to create a scatter plot. Which better represents the data, a line or a parabola? Explain. Well, I'm guessing a parabola based off the gravity thing. But who knows how sponges fall. So we'll see. I'm going to plug these values in. I see the calculator on the screen. I don't see. All right, here we go. Well, I'm going to plug these values in, and we're going to go to Stat and Edit, and we're going to get, let's see, 0, 1, 1.5, 2.5, and 3. And then the Y values are 280, 264, 244, 180, and 136. Okay, so from here, listen, my calculator resets itself each time, so I actually have to go to Catalog, and I have to go to Diagnostic On. Where's D? Right there. I have to go to Diagnostic On if I want to check, if I want to get every such value that I need. I don't know for sure. And I need to turn Stat Plot on here so that I can look at my data points. Now my data points go from 0, I'll plug in a -2 just to kind of be fair here, -2 to say 5, and the Y values go, not even from 0 to anything, but I'll go from 0 to 300. So let's look at the values and see what we see. You might argue linear, but remember, here's the first point. That's the first point right there. I'm going to argue quadratic for sure. A parabola looks like parabolic in nature. So as far as that part A goes, I mean, they're asking which better represents the data, a line or a parabola. Explain. A parabola. There's a curve. So part A, parabola. It has a curved nature, and the sponge is probably falling faster as time goes on due to gravity. The force of gravity, right? So we'll see how that actually pans out, as the other parts are probably going to ask us to make an equation. Part B, yes, use the regression feature of your calculator to find the model that best fits the data. So we're going to, if we said parabola, we're going to use quadratic regression. So I have the data points. I'm going to go to Stat and Calc, and here's where we use quad reg. So quad reg is going to be used on lists L1 and L2 automatically, and we get these numbers. Oh, they're exact. And look, A is -16. That's nice. So it looks like the vertex was actually that 0, 280. So our equation for part B is going to be y equals -16x squared plus 280. The r squared is 1, which means this was a perfect scatter. This wasn't even a scattered scatter. You know what I mean? These are perfect points to go through the quadratic. This wasn't an estimate. Anyway, I didn't know that. So this is going to be y equals -16x squared plus 280. Not even approximate, it's exact. And part C, use the model in part B to predict when the sponge will hit the ground. So now we got to find out when y is 0. What value of x gives us a value of y for 0? 0 for y, I should say. I can add 16x squared to both sides, which basically makes that one positive alongside this one. Divide by 16, and then take the square root of both sides. So square root of, well, let's do this. 280. Let's do 280 divided by 16. I don't know what it is. 17.5. We'll take the square root of 17.5, and it's around 4.183. It's going to hit the ground after 4.183 seconds. I don't know how many things I should round to, so I'm just going to put that. 4.183 seconds later, it should be hitting the ground. Oh, this was T and H. Let's change all that. Can I change these really fast? Is that okay? T's and H's, y'all. All right, so this was H of T, and this is T. T, T. All right, cool. Okay, so that's the time that it's going to be hitting the ground after that. And that kind of seems like it makes sense, right? It's hasn't hit the ground yet, but it's speeding up. We got to get another full second in and then some. I believe it. Part D, identify and interpret the domain and range in this situation. Well, I'm not going to draw the graph there, but if you go back to the graphing calculator, you can see based off the graph here, this is the start of when it drops, right? It drops there, and then it's going down, hits the ground. Keep in mind, it's not going outward. This is as time goes on. Now, as time goes on, it hits the ground. Once it hits the ground, it stops falling, right? Kersplat. So the model stops once it hits the ground. So for us, our domain is when we drop it at time 0, all the way to the 4.183 seconds that we're about. The range is from the top height. The top height is 280 feet. Oh, that's not a top though. The bottom is 0 when it hits the ground. So 0 is the low, and 280 is the top. Is it in feet? Yes, in feet. Interpret. So domain is the time. The domain is the, I was going to say the range, is the interval of time in seconds when the sponge is falling. And the range is the interval, is the height, represents the different heights of the sponge, of the falling sponge, and in feet. Okay. All right, so there's part D, and that's the finished part of the problem. All right, number 28. Making an argument. Your friend's been wrong a bunch. They got to be right at some point. Let's see if it's now. Your friend states that quadratic functions with the same x-intercepts have the same equation. Oh, friend. The IM3 friend is having trouble. Same equations, vertex, and axis of symmetry. Is your friend correct? Explain your reasoning. Not only is my friend incorrect again, I think he's 0 for the chapter, dude. My friend is incorrect. Not only is my friend incorrect, I believe this was in the last section. I think this was kind of like the last question on the last section as well. I'm going to disprove by counterexample. I'm going to show my friend is wrong with a counterexample. It says explain your reasoning. Here's my explanation. Friend, I can have these two intercepts. Here can be a graph. Well, also, here can be a graph with those two intercepts. And also, here can be a graph with those two intercepts. These have different vertexes. Just because they have the same intercepts, they're not necessarily the same equations or vertexes. They will have the same axis of symmetry, however. I should mention that. They will, however, have the same axis of symmetry. Okay? Because they all have that symmetry right through there. Outside of that, different equations, different vertexes possibly. You can have the same intercepts, but a different A value will change things. And that's really what that last question was about on the last section. All right, numbers 29 to 32, we're going to analyze the differences in the outputs to determine whether the data are linear, quadratic, or neither. Explain if linear or quadratic, write an equation that fits the data. So probably a lot of work to do when it's a quadratic answer. I'm going to copy paste these tables. You know what we're looking for? Once again, we're looking for linear is going to have a constant difference, constant first difference. Quadratic is going to have a constant second difference. A neither will be a neither. And I guess they're supposed to be exact. So we're going to get those tests. From 470 to 630, we're adding 160. Here we're adding 60, so it's clearly not linear. And then we're subtracting 40, and then we're subtracting 140. Okay, let's see if it has a constant second difference. From 160 to 60, that's minus 100. And that's, yes, minus 100, minus 100. So this is quadratic, which means we're going to have to deal with big numbers here to solve this system. I got to use 3 different sets of points. I'll just use the first 3 right here. And we're going to set up a system of equations. Hopefully you know what we've been doing with this. The whole y equals ax squared plus bx plus c. And I see no such indication of a vertex. It's somewhere between 5 and 15. I don't know where. But I got to plug these in. Thankfully, c will be solved for here. 0 squared times a plus 0 times b plus c equals 470. Now, if c equals 470, I'm going to substitute that. I'm going to substitute it immediately. Is that okay? If c is 470, let's substitute it into the next one. We get 25a plus 5b plus 470, that's c, equals 630. And then 10 squared is 100a plus 10b plus c equals 690. So there's my initial setup for those. Let's subtract 470 over on these. And we get, you can tell I want to divide by 5 on this one, probably divide by 10 on the next one. Subtract 470 and you get, I think that's 160. So if I divide by 5, make sure that's 160 first. Yep. Divide by 5, we get 5a plus b equals 32. Now on this other equation, where I'm soon to divide by 10, let's actually divide by 10 now. No, let's divide by 10 after. 100a plus 10b equals, and that's 220. Now as I divide by 10, we're going to get 10a plus b equals 22. If I subtract right now, let's just kind of treat it like subtraction. If I subtract right now, those go away. You get negative 5a equals 10, and you get a equals negative 2. So we've got an a value of negative 2. We have a c value of 470. We can find b by any of these equations. I like the 5a plus b equation. That's negative 10a, so negative 10, excuse me, negative 10 plus b equals 32. So b equals 42 when we add 10 over. So your equation, they just said write an equation that fits the data. This equation will be y equals, and by the way, I didn't look at the, they're not asking about the representation or anything like that. This is thousands of dollars of revenue based on a price decrease in dollars. I'm not looking at any of that for now unless they ask me to interpret. But y equals negative 2, that's our a value, negative 2x squared plus 42, that's bx plus c, which is 470. So there is the quadratic that fits that. Now, I could have chosen any of the points on here. I decided to choose those 3. You need 3 of them, though, for the system of 3 to find A, B, and C. All right, let's go to number 30. And I think I have the room on number 30 because number 30 is already looking pretty linear. You okay with me leaving it over there? On number 30, oh, they said explain. Hold on. Constant second difference. Here's my explanation. Quadratic. Because look at that. Okay, so maybe I do have to copy paste here. So number 30, I'm looking at something that looks pretty linear. Pretty linear. And this will be a very fast equation to write as well. It's all about slope and y-intercept, right? Slope and y-intercept. So number 30, we have a constant first difference of 2, adding 2 each time, as x keeps increasing by 1, no less. We have to keep that in mind, right? I should have mentioned that for number 29. That's a constant increase of 5 right there, which allows us to check this constant increase as well. That's the important part. So this is making this linear. Because of that, we have something linear. Now we need to make an equation. The slope is 2. As x increases by 1, it's up 2 over 1. So y equals 2x. Y-intercept is 40. So y equals 2x plus 40. That's it, and that's all. Nothing else to do on that one. Number 31. Well, number 31 actually doesn't look linear or quadratic. I want to just bring up kind of what it is. They don't ask us to write an equation in this one, but I can for you because it looks like it's an exponential equation. So I don't know how versed you are in exponentials. You did do them in IM1 and IM2. You will do them later in IM3 when we do logarithms, I'm sure. But let's talk about that, right? Doesn't have a constant first difference. That's plus 2. But by the way, these are going up by 1s. This is plus 2, plus 4, plus 8, plus 16. Doesn't have a constant second difference. That's plus 2, plus 4, plus 8. That doesn't seem to change what it's doing. So neither, because here's what we're seeing. But here's what it is doing. Times 2, times 2, times 2, times 2. It's a common ratio or a growth factor of 2, if you will. When it comes to these, you'd also want a y-intercept. The y-intercept here is when x is 0, so 1 times 2 would give you that. So with a y-intercept of 1, this is all about your y equals ab to the x form. I know they don't necessitate this equation, but that's y equals 1 times 2 to the x power, or y equals 2 to the x power is basically that answer. So I know they don't want that, or they're not asking for it, but that is it. Okay. Let's go to number 32, last one in this block. And then we'll have 5 more problems to go, which means at this stage we have 6 more problems to go. All right. And given that we've been in a section of quadratics, I wouldn't be surprised if this was a quadratic. Is that a common difference? That's not a common difference. So yeah, this is probably a quadratic one. Let's see. All right, let's check this one out. We got first difference of minus 17. Oh, that's a big jump from 1, 2, 3, 4. This is minus 17, then minus 59. Is that right? Then minus 81 and minus 113. Let's see if that's a common difference. Otherwise, I might have messed up on my numbers. Minus 42. Minus 42. Oh, that's minus 32. Hold on. This must be minus Wait. Minus 42. Why did it say minus 42 here? From negative 59 to negative 81, that's minus 22. Hold on. Is this anything? 320. Let me do this on the calculator. I might have totally messed up here. 320 minus 303. I don't know why I'm having trouble with that. Is 17. 303 minus 254 is 49, not 59. Okay. 49. Okay, that actually explains a lot. So this is now minus 32. And that's minus 32. Okay, that works. I was like, minus 42, minus 22, minus 32. No. Something's going wrong. All right, much better. All right, it's quadratic. It's constant second difference. Kind of what I expected. Otherwise, it's just topsy-turvy nothingness. I don't know what to say on that. All right, I got 3 points I got to choose. I'm going to choose this one because I got 0. I'm going to choose this one because I get 1. I'm going to choose this one because they're small. 60 small. I don't think it matters for 60 to be small. I don't think that's helpful. I think it helps that x is small and these numbers are close. I'll be honest. So I'm going to choose the first 3. And you're wisest to do that as often as you can. So this is one of those, again, 0 squared. Again, I'm going to write this out. I think it's as helpful for me as it is for you. But 0 squared times a plus 0b plus c equals 320. And now that we know c is 320, again, I'll substitute into these. 1a plus 1b plus c equals 303. And then 2 squared a plus 2b plus c equals 254. Yeah, I think it's better that we use these numbers. Otherwise, we got to do 4 squared and stuff like that. I think this is just best. Subtract 320 over. You get a plus b equals negative 17. And then subtract 320 over. You get 4a plus 2b equals... I'm having trouble. Negative 66? I think negative 66. If I divide those by, let's say negative 2, you get negative 2a minus b equals 33. Now ignore that one as we add down these lists here for elimination. These go away. Negative a equals 16. So a is negative 16. Hey, it might be a gravity-like equation. Yeah, time and days and height and feet. For some reason, height goes down in gravity every day for something. So I hope I did that right. But then I get negative 16 there. If a is negative 16, then b, negative 16 plus b is negative 17. B is going to be negative 1. So my equation now with the 320 will be y equals negative 16 x squared minus x minus b times x plus c plus 320. And 320, therefore, is the y-intercept. Not the y-intercept, is the vertex. Yeah, it's the y-intercept. I don't know if it's the vertex, but it's the, it's not the vertex, but it's the y-intercept of this thing. I'm speaking too much. Okay. Let's go to, hold on, I lost my thing. Let's go to number 33. Problem solving. The graph shows the number y of students absent from school due to the flu each day x. Oh, I thought it was like cutting or something like that. Due to the flu. Okay. Interpret the meaning of the vertex in this situation. So 6 days in, you have the maximum number of students that's absent, which is 19. That's what I'll say. 6 days what? Into the school year? Into the epidemic. 6 days into the flu epidemic is when the school sees a maximum number of students absent from the flu at 19. So 19 students are absent from the flu. That's the max number that you have. Part B. Write an equation for the parabola to predict the number of students absent on day 10. Now we can look at the model for day 10 absences, and it's going to be somewhere about probably 11 students. That's probably what I'm looking at there. But we're going to go ahead and use this vertex form stuff for this. So we got a vertex of 619. We got a point on here that is 0, 1. And we're going to substitute those in. Or you can use my conventional version, right? We're going over 6. Normally we'd go up 36. Now we're going down 18. Well, that's half of 36. And because we're going down, that means it's negative 1/2. So I know the equation is going to be negative 1/2 times x minus 16, x minus 6, excuse me, squared plus 19. You'll be wise to remember that when we get the answer. Okay, so let's get that out of view there, or down lower. So we're going to do y equals a times x minus 6 quantity squared plus 19. Let's substitute 1 for y, 0 for x. That's negative 6 squared plus 19. 1 minus 19 is negative 18. 36a. Divide both sides by 36. You get a is negative 1/2, and that goes down there. So we got that. It's not the final answer. We're predicting on day 10. So we're going to do now y equals negative 1/2 times 10 minus 6 squared plus 19. 10 minus 6 is 4. 4 squared is 16. Half of 16 is 8, so that's negative 8 plus 19, which is 11. So yeah, 11 days. That's what I thought it was going to be. So 10 days into the flu, 11 students are sick. They're absent. Okay. Part C, compare the average rates of change in the students from the flu from 0 to 6 days and 6 to 11 days. So this is where we're talking about slopes, right? They say average rate of change. All they mean is slope. All they mean is what's this slope here and what's this slope here. Give me a second. I'm trying to do a different color. And what's this slope here? That's all they want to know. Don't get it any more confused. We can do y2 minus y1 over x2 minus x1, or maybe you're really good at counting in different ways here as well. So let me just kind of use the side of the screen here and just answer some of that stuff, right? What's the rise? Well, we talked about this. It's rise of 18 and it's a run of 6, right? We rise 18, we run 6 from here to here. Let me use that color. Give me 1 second. From 1 to 19 is a rise of 18, so 19 minus 1, 18 over 6 minus 0 is 6. That slope, average rate of change, is 18 over 6, which is 3. For this one here, you're going down. You're going down, son. This point, by the way, is 10, 11. You're going down from 19 to 11, that's 8. You're going over from 6 to 10, that's 4. And the slope there is negative 8 over 4, which is negative 2. On average, that's the increase. On average, that's the decrease there. So I wrote the work on that side. It is a rise over run thing, but that's what we're doing. So comparing the average rate of change. So three new students per day, sick on average here and there. So they said compare them. So the slope going up is 3. Slope going down is negative 2. Absolute value of 3 is greater than the absolute value of negative 2, which is to say more students were getting sick per day on average. More students were getting sick per day on average from day 0 to 6 than there were not getting sick, healing, recovering. I mean, this is about them coming back to school, really. But then there were recovering on average from day 6 to 10. Okay, it's kind of the idea. I'm really bad at typing those things, at least on the spot. But hopefully that clarifies what you're trying to look to do. Okay, 4 more questions. Number 34. Can I break the 2-hour mark? We'll see. Thought-provoking. Describe a real-life situation that can be modeled by a quadratic equation. Justify your answer. Well, they did a lot of gravity ones. They did a temperature one. Real-life situation can be modeled by a quadratic equation. They've done area ones. I want to do like a profit one or something like that. Let's see. I mean, I do quadratic word problems all the time, and for some reason I can't just think of one. Yeah. I'll do a profit one. So, profit equation. So, this is basically price point So what I mean by this is when you set too low of a price, of a selling price for an item, you may get more sales, but not enough, but not enough return per item to get enough profit. And remember, profit includes costs, so there's that involved as well. Likewise, if you price an item too high, you won't get enough sales for some profit. There is a balance. There is some in between. There may be some in between compromise of a price point that'll maximize profit, which is what all businesses try and do, right? All businesses try and do this, right? You sell video games for $60, $70, whatever it is. That's because that's what people are willing to spend in the thing. If you do it for $30, great, more people will buy it, but you don't get as much money in return. And you get it at $100, less people will buy it, that kind of thing. Plus, it's probably just a standard. All right, so anyway, there's that idea, right? But so the X would have been the price point, the Y would have been the profit, and somewhere it's like, you know, you get no return versus you get some return. There's some maximum there that you do. We kind of had some questions like that. I think they had to do with revenue, but I'm not coming up with an actual model of it right now. Anyway, number 35 on problem solving. The table shows the heights y of a competitive water skier x seconds after jumping off a ramp. Write a function that models the height of the water skier over time. When is the water skier 5 feet above the water? How long is the skier in the air? Do we know that this one is a for sure, like, should I use the graphing calculator? Or am I supposed to use a system of 3? Let me pause for a second. I'm going to type it in the graphing calculator, see if it's exact numbers. If it's not, I'm going to use the system, if it's not, we're going to leave the calculator answer. If it is exact answers, I'll do the system of 3. Give me a second. Okay, so I went to the calculator, and here's what it reveals when I plot in the points. Exact numbers. So it looks like we're going to have to probably do this together. But these are the numbers we expect to get. Negative 16x squared plus 6x plus 22. So let's go ahead and try that for ourselves freehand. That means this is a quadratic, by the way. I think we understand that because this is height of a skier and stuff like that, they'll have a parabolic, jump and stuff. And in fact, I expected A to be negative 16 because of the gravity stuff, right? We see that quite a bit. But we still got to choose 3 points. Now, which points to choose? Probably wouldn't be caught dead using the one with 9.24. Kind of like that one because the numbers are clean enough. Definitely like that one. Let's go smaller first, I guess. 0.25. Sure. Okay, so we're going to choose 3 of these points. First one will give us, you've seen this a lot, a C value of 22, because when x is 0, the others wipe out. 0.25. 0.25 squared is 0.625, I think. I got to check that. I got to see if the decimal's right. I know it has those numbers, but 0.25, whoops. 0.25 squared. Oh, 0.0625. See, I didn't want to mess up. So I'd rather use the fractions. 0.0625. In fact, let's use the fraction. This is 1/4, and 1/4 squared is 1/16. 1/16 times A plus 1/4 times B plus C, 22, equals 22.5. I'll show you what I'm going to do with that in a bit. That's not going to be too much trouble. And 1 squared times A plus 1 times B plus C equals 12. Okay, with this one, I have 1/16 A plus 1/4 B. You subtract 22, you get 0.5. 0.5 is 1/2. But if I multiply everything here now by 16, now this stuff will clean up for me. Now I'm going to get A plus 4b equals 8. There. Now that's a lot cleaner. And then I still have my a plus b here equals, and 12 minus 22 is negative 10. Now if I want to eliminate something such as a, let's change this negative, and this positive, and eliminate, and we get 3b equals 18, so b equals 6. According to my calculator, b equals 6 was a correct answer on that thing. To solve for a now, we have an equation that says a plus b equals negative 10. B is now 6. Let's just turn it into that. and subtract 6, you get a is negative 16, kind of an expected value from that because of gravity, and c is 22. So we now have an equation y equals negative 16 x squared plus 6x plus 22, which is the same from the calculator. There hasn't really been a problem. Maybe it's showing up in 2 more questions, but there hasn't really been a problem yet that we've had an actual scatter plot of data off the quadratics, that it wasn't perfect values. Even the one that they said use the calculator for was perfect values. Anyway, they say, when is the water skier 5 feet above the water, and how long is the skier in the air? So we saw we saw a question like this before, probing these things in that kind of way. So when are they 5 feet in the air? We set this equal to 5. Now we're going to, I doubt this is factorable, plus 6x plus 17 equals 0. I'm going to make a full-on assumption that's not equal, it's not factorable, but I'm going to divide by negative 1. Let me make sure. Yeah, that's not factorable. So I don't even want to use completing the square, guys. I'm going to go straight to quadratic formula on this one. I start with the discriminant of b squared minus 4ac. If you've been with me before, you know what I'm talking about. So b squared minus 4ac is going to be 36 plus, calculator, come and get me, 1088, which is 1,124, which I don't believe is a perfect square. Let's see. Well, it can't be a perfect square, otherwise it would have been factorable. It's not. So anyway, x equals negative b, that's positive 6, plus or minus the square root of 1,124 all over 2a, that's 32. So these are the 2 different values that we have here. 6 plus root 1124 over 32, 6 minus root 1124 over 32. So I'm going to calculate both of those. I'll show you on the calculator what I'm going to do with those. Actually, let's do this. Let's do what I did before, one minus the other. So like x equals 6 plus, right? This is the bigger time, minus that. And what happens here is what you saw before. The 6's will cancel. The 1124's will add up together, right? Because you got to distribute this negative. So the 6's will go away, and the 1124's will double up. So x is going to be 2 root 1124 over 32, which is root 1124 over 16. And I'm sure this simplifies to something in such a way that I can keep reducing the fraction, but we got to get to the calculation at some point. So I'm going to do that right now. Root 1124 divided by 16, and I'm getting around 2.095, so around 2.1 seconds. That the water skier is above 5 feet in the air. 5 feet above water, I should say. 5 feet above the water. All right, so that's one of them. The next one, I'm just going to copy and paste this equation, use it on the other side. They say, how long is the skier in the air? So now we're going to set that equal to 0, and we're going to apply the same thing that I mentioned previously, which is setting this equal to 0. We're going to solve for x, but what you want to keep in mind here is the water skier starts 22 feet in the air, right? They start here, and then it goes up and down, whatever. So we got to go from 0 to whatever this version of this number is. Now I'm going to divide everything here by negative 2 because I can. I'll get 8x squared minus 3x minus 11 equals 0. Is that factorable? I always want to check in my head. This might be factorable. Hold on. 8x x minus 11 and plus 1? Does that work? 8x squared plus 8x minus 11 is minus 3x minus 11. That's actually factorable. Cool. All right, well, that's good. Now you use zero product property. Either x equals negative 1, which isn't allowed, or 8x minus 11 equals 0. So 8x equals 11, so x equals 11/8, which I think is exactly 1.375. So for 1.375 seconds, something sounds wrong about that, though. Let me think about that. Let me also think about the 5 feet in the 5 feet above the water thing as well. Hold on. Water skier, X seconds after jumping off a ramp. Models the height of the water skier. When is the water skier 5 feet? Oh, when is the water skier 5 feet above the water? Oops. Hold on. This answer isn't what this is. Let me go back to this part. When is the water skier 5 feet above the water? It's just the plus because it's the same thing. As I look at the table, X equals just 6 plus root 11, 24. Sorry about that. I thought it was for what interval are they 5 feet above and below or whatever that kind of thing that we had before. This question, they aren't 5 feet above on a second part over there. It's just on this part. So let me recalculate this, then I'll go back to the other question because I don't know if the other answer is correct unless I see this number properly. 6 plus root 1124 divided by 32. Okay, 1.235. All right, that looks a little better. 1.235 seconds. Now let's check that other number and see if it looks okay. 1.375. Okay, at least that number looks better because I said, how can I be above 5 feet for more time than I'm above water in total? That didn't make any sense, and I think I just clarified my own question by doing that part. So 1.375 seconds is exact. That's not even approximated one based off that for the water skier. Okay. 2 more questions. Number 36. Use the graph. How do you see it? Use the graph to determine whether the average rate of change over each interval is positive, negative, or 0. I'm going to totally go based off how I see it and draw little lines on them. From 0 to 2, all we got to do is look at when x is 0 to when x is 2 and look at that kind of slope. So for part A, from 0 to 2, that is a positive slope. I'm speaking my northern accent. It's a positive slope. All right, B, from 2 to 5. Here's where x equals 2. Here's where x equals 5. That is a negative slope. Negative rate of change. That's all we care about. Whoops. 2 to 5 is negative. On average, from 2 to 4. Well, not much different from 2 to 5. Boom, still negative. So from, watch this. From 2 to 4 on C, still negative. Okay. And for D, from 0 to 4. Here's 0. Oh, yeah, here's 0, here's 4. See, it made changes, right? It went up, we went back down, but on average, they canceled each other out, ultimately, right? It looks weird to say that, but that's how average rate of change works. On average, what'd you do? It's like, I made $80 and then I lost $80. On average, I made $0. That's just how it works. So a 0 slope on that. Okay, and then the last question. Can I break 5 minutes on it? Let's see. Number 37. Repeated reasoning. The table shows the number of tiles in each figure. Verify that the data show a quadratic relationship. Predict the number of tiles in the 12th figure. Okay. I used to do tile things. I used to do what was it called? Number sense? I think we used to do number sense daily openers or something like that in class. And we used to say predict the number of tiles, not based off the table, but based off the patterns on the tiles. So I wonder if I'm supposed to use tile patterns to work on this, because I see some information, guys. I see some things I can do with the tiles. But here I got a +4, +6, +8, and those have a common difference of 2. So that shows that it's quadratic. So verify the data's quadratic relationship. Verified. Quadratic. Check. Now, listen, I look at these tiles and I see some stuff. Two squared, 3 squared, 4 squared, plus 1 minus the other number. I'm guessing my relationship here is y equals x squared plus your number minus 1. X squared plus x minus, this is my guess for the equation based off the pattern relationship. 4 squared plus 4 minus 1. 3 squared plus 3 minus 1. 2 squared plus 2 minus 1. 1 squared plus 1 minus 1, 0. Okay, that's my guess. But we got to do this based off of standard form. 3 parts here, right? So let's see if this ends up being the answer. Now, let's check it out. We got 1a plus 1b plus c equals 1. We got 4a plus 2b plus 1c equals 5. Hopefully you know how I'm doing this. Squaring my x for a. 9a plus 3b plus c equals 11. Okay, this is more of a system of 3 that we actually got to work out. The other ones really turned into systems of 2 because I got to cancel out some c's. Let's turn these ones negative here and cancel out them with the other two things. So like right here, put these two together, combine them, we get 3a plus b, c's cancel, and that equals 4. And then put these two together, and we get 8a plus 2b equals 10. If I divide this by -2, I get -4a minus b equals -5. Sorry if my work gets roughed out on these stages. This is where I just get a little more like, yeah, I'm doing my own thing. 3a minus 4a is -a. 4 minus 5 is -1. If -a is -1, then a is 1. All right. If 3a plus b equals 4, then 3 plus b equals 4. Therefore, b equals 1. And if a plus b plus c equals 1, if 1 plus 1 plus c equals 1, or 2 plus c equals 1, then c equals -1. So my final equation will be y equals 1x squared plus 1x minus 1. What did I say it would be? 1x squared plus 1x minus 1. Awesome. There's my equation. Predict the number of tiles in the 12th figure. Well, it would be 12 squared plus 11, so 140, so 155. So 12 squared plus 12 minus 1. Oh, I guess we're calculating that anyway. 144 plus 11, which is 155 tiles. All right. That's the last question. And guys, that'll do it for this one. I beat the 2-hour mark. This is Mr. Robinson. Thank you so much for watching. We finished the chapter. Now we have chapter 2 review and chapter 2 test and cumulative assessment. Thank you so much. Take care. I'll see you in the next one.